Okay, this is going to be over sections 14.4 through 14.6. We're going to discuss heat, phase changes, and calorimetry. So, heat is energy transferred from one object to another as a result of a temperature difference. The quantity of heat, Q, required to raise the temperature of a mass M of material by a small amount, delta T, is related as follows. Q is equal to mc delta T. C is going to be the specific heat of the material. So to change a mass M of a material to a different phase, such as liquid to solid or liquid to vapor, at the same temperature requires that the addition or subtraction of a quantity of heat, and it's going to be given by plus or minus M times L. L is going to be the latent heat of fusion, the latent heat of vaporization, depending on which way you want to go, or the heat, the heat of sublimation. Calculations with heat are called calorimetry calculations. In an isolated system whose parts interact by heat exchange, the algebraic sum of the Q's for all parts of the system must be 0. In other words, it's the system is not losing or gaining heat, so it's got to be the same. But different parts of the system might be gaining at the expense of others. So this particular graph is going to show you the temperature and time. And what you're going to see here is if you have ice that is warming and eventually gets to 0 degrees Celsius, it's going to remain at that particular temperature until all of it is transitioned over into water. That liquid water is going to then warm, and then in order for the liquid water to vaporize into steam, it's going to take a little bit of time here, but eventually, once all of it is changed over in this phase change, then you can see the steam being warmed as well. So let's take a look at section 14.4 here. Okay, I'm not going to play the video here, but these demos would be of value to you. So again, we're going to discuss heat transfer when something is being transferred between two different objects. So Sir James Joule discovered that water can be warmed by vigorous stirring with a paddle wheel, if you look at a device such as this. And the rise in temperature is directly proportional to the work done and the energy added in turning that wheel. Since the same temperature change could have been caused by putting the water in contact with some hotter object, in other words, the mechanism could be different, but the effect is the same, that interaction must involve an energy exchange. And this experiment and many similar ones have established the fact that heat flow is energy transfer and that there is an equivalence between heat and work. The same change of a state of a system, such as change in temperature or volume, can be produced by heat flow, work, or a combination of the two. So here you can see in this particular picture, you're raising the temperature of water by doing work on it. So you've got a weight that's attached here to a pulley around threadings, and then you've got a paddle. So the water warms as the paddle does work on it. The temperature rise is proportional to the amount of work done. Raising the temperature of water by doing work on it. Direct heating can produce the same temperature change as doing work on the water. Doesn't matter which mechanism you use here. Energy transferred in this way that takes place solely because of a temperature difference is called heat. So for example, cold water in a steam boiler is converted to steam by contact with a metal pipe kept at a higher temperature by a hot flame from burning coal or gas. Having received energy from the flame, the water as steam has a greater ability to do work by pushing against a turbine blade or the piston in a steam engine. Rather, or that than does an equal mass of cold water. Just as we cannot define the amount of work in an object, we also cannot define the amount of heat in an object. The concept of heat has meaning only as energy in transit. The entire quantity doesn't mean anything, but how much is transmitted does. So a detailed study of the relationship between heat and work leads to the first law of thermodynamics, which we're going to get into in chapter 15. Because heat is energy transferred from one system to another, the SI unit of quantity of heat is going to be the joule. The IC on weight and measures recommends use of the joule as a basic unit of energy in all forms, including heat. We'll follow that recommendation in this book. However, several older non-SI units are also commonly used for heat. One of those is the calorie. The calorie, abbreviated CAL, is defined as the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. The familiar calorie found on food labels is actually a kilocalorie, equal to 1,000 calories. A quantity of heat energy can be converted into other forms of energy, such as kinetic energy. A corresponding unit of quantity of heat that uses Fahrenheit degrees in British units is the British thermal unit, or BTUs. So 1 BTU is defined as the quantity of heat required to raise the temperature of 1 standard pound weight of water 1 Fahrenheit degree, from 63 degrees Fahrenheit to 64 degrees Fahrenheit. Because heat is a form of energy, there must be a definite relationship between the preceding units and the familiar energy unit, the joule. If you do the experiments, you can see the equivalent units here. Packaged foods sold in many countries outside the US list the energy content in joules as well as calories, which myself, not having traveled too much outside the US, I didn't know that. Specific heat. So we use the symbol Q for the quantity of heat that is transferred from one object to another. The quantity of heat Q required to increase the temperature T of a mass M of a certain material by the small amount from T1 to T2 is found to be approximately proportional to the temperature change. So to raise the temperature of a certain mass of a substance from 20 degrees Celsius to 40 degrees requires approximately twice as much heat as the amount needed to raise it from 20 to 30. The heat required for a given temperature change is also proportional to the mass M of the substance. Thus, when you heat water to make tea, you need twice as much heat for 2 cups as for 1 if the temperature interval is the same. Finally, the quantity of heat needed also depends on the nature of the material. To raise the temperature of 1 kilogram of water by 1 Celsius degree requires almost 5 times as much heat as for 1 kilogram of aluminum at the same temperature change. So if you put all those together, this is the formula you come up with. Q is going to have units of joules, and your specific heat is going to have units of joules divided by kilogram times Kelvin. Q is going to be positive if heat is transferred to the object, and negative if heat is removed from the object. When heat energy is transferred to an object, the temperature goes up and delta T is positive. Likewise, if heat energy is removed, delta T is going to be negative. The specific heat of water, 4190 joules per kilogram Kelvin, or 1 calorie per gram Kelvin, or 1 BTU per pound Fahrenheit degree. Specific heats vary somewhat with the initial temperature and the temperature interval. For example, the specific heat of water varies by almost 1% in the temperature range from 0 to 100 degrees Celsius. We're usually going to ignore this small variation. So you see a list of things there. And again, I would encourage you to go through the problems. Now, note, remember the distinction between temperature and heat. Temperature depends on the physical state of the material and is a quantitative description of its hotness or coldness. Heat is energy transferred from one object to another because of a temperature difference. We can change the temperature of an object by adding heat to it or taking heat away from it, or by adding or subtracting energy in other ways, such as doing mechanical work. If we cut an object in half, each half has the same temperature as the whole, but to raise the temperature of each half by a given interval, we add half as much heat as for the whole. So now let's go to section 14.5. Phase changes. So we've discussed the energy transfer heat involved in changing an object's temperature. Turns out that heat is also involved in phase changes, in which a substance changes from a gas to a liquid, or perhaps from a liquid to a solid. Examples include the melting of ice and the boiling of water, where liquid water is turned into steam. So we use the term phase to describe a specific state of matter, such as solid, liquid, or gas. The compound water exists in the solid phase as ice, in the liquid phase as water, and the gaseous phase as steam. The transition from one phase to another is called a phase change or phase transition. For any given pressure, a phase change usually takes place at a definite temperature and is usually accompanied by the absorption or emission of heat and a change in volume and density. So a familiar example of a phase change is the melting of ice. When we add heat to ice at 0 degrees Celsius and normal atmospheric pressure, the temperature of the ice does not increase. Instead, some of the ice melts to form liquid water. If we add the heat slowly to maintain the system very close to thermal equilibrium, the temperature remains at 0 degrees Celsius until all of the ice is melted. The effect of adding heat to the system is not to raise its temperature, but to change its phase from solid to liquid. In other words, it takes heat energy to disassemble the crystal structure of the ice. So to change 1 kilogram of ice at 0 degrees Celsius to 1 kilogram of liquid water at 0 degrees Celsius and normal atmospheric pressure requires 3.34 times 10 to the 5th joules of heat. The heat required per unit mass is called the latent heat of fusion and denoted by L sub F. The latent heat of fusion of water at normal atmospheric pressure is this. More generally, to melt a mass m of material that has a latent heat of fusion requires a quantity of heat given by this. It's basically the product of the mass times the latent heat of fusion. The process is reversible. To freeze liquid water, we have to remove the heat. So the magnitude's the same, it's just that the sign for Q is going to be negative. At any given pressure, there is a unique temperature at which liquid water and ice can coexist in a condition called phase equilibrium. The freezing temperature is always the same as the melting temperature. We can tell this whole story again, changing the names of the characters for boiling or evaporation, a phase transition between liquid and gaseous phases. Corresponding heat is called the latent heat of vaporization. At normal atmospheric pressure, the latent heat of vaporization is going to be this. Note that more than 5 times as much heat is required to vaporize a quantity of water at 100 degrees Celsius as to raise the temperature from 0 to 100 degrees Celsius. So both L sub V and the boiling temperature of material depend on the pressure, just like it did for the latent heat of fusion. Water boils at lower temperature in Denver than in Pittsburgh because Denver is at a higher elevation and the average atmospheric pressure is lower. The latent heat of vaporization is somewhat greater at this lower pressure. Like melting, boiling is a reversible transition. When heat is removed from a gas at the boiling temperature, the gas returns to the liquid phase or condenses, giving to its surroundings the same quantity of heat as was needed to vaporize it. At a given pressure, the boiling condensation temperatures are the same. And there's the summary of the latent heat of fusion or latent heat of vaporization, depending on what phase you're changing to. Mass is the material, m is the mass of the material undergoing the phase change. Plus or minus refers to the fact that the changing to solid to liquid or liquid to gas, heat energy must be added and Q is positive. For going the other direction, heat must be removed. We can look at heats of fusion and vaporization for some materials with corresponding melting and boiling temperatures at normal atmospheric pressure. Very few elements have melting temperatures in the vicinity of ordinary room temperatures, but one of the few is the metal gallium. So this figure shows how temperature varies with time when heat is added continuously to a specimen of ice with an initial temperature below 0 degrees Celsius. Temperature rises from A to B until the melting point is reached. Then as more heat is added, the temperature remains constant until all the ice is melted. And then next, the temperature starts to rise again until the boiling temperature is reached. At that point, the temperature is constant until all the water is transformed into the vapor phase. If the rate of heat input is constant, then the slope of the line for the liquid phase is smaller than that for the solid, because as the table indicates, the specific heat of ice is only about half that of liquid water. A substance can sometimes evaporate directly from solid to the gaseous phase. This process is called sublimation, and the solid is said to be sublime. The corresponding heat is called the latent heat of sublimation, or L sub S. Liquid carbon dioxide cannot exist at a pressure lower than 5 times 10 to the 5th pascals, or about 5 atmospheres. So dry ice sublimes at atmospheric pressure. Sublimation of water from frozen food can cause freezer burn, and is the reason clothes can dry on a clothesline even at sub-freezing temperatures. The reverse process of phase change from gas to solid occurs when frost forms on cold objects, such as the cooling coils in a refrigerator. The temperature control mechanism of many warm-blooded animals also makes use of the latent heat of vaporization, removing heat from the body by sweating or panting, both of which depend on the evaporating water from the body. Evaporative cooling enables humans to maintain normal body temperature in hot, dry desert climates, where the air temperature may reach 55 degrees Celsius or about 130, think Death Valley. The skin temperature may be as much as 30 Celsius degrees cooler than the surrounding air. Under these conditions, a normal person may perspire several liters a day. Unless this water is replaced, dehydration, heat stroke, and death result. Bad things. Evaporative cooling is also used to cool buildings in hot, dry climates and to condense and recirculate used steam in coal-fired or nuclear-powered and electric generating plants. And that's what's going on in the large cone-shaped concrete towers that you see at such plants. Chemical reactions such as combustion involve definite quantities of heat. Complete combustion of 1 gram of gasoline produces about 46,000 joules or 11,000 calories. So the heat of combustion of gasoline is as follows. So earlier we had mentioned that the energy value of food is measured in kilocalories, where 1 kilocalorie is 1 calorie or 4186 joules. When we say that a gram of peanut butter contains 6 calories, we mean that if we burned it up completely, allowed it to undergo complete combustion with oxygen, it would release 6 kilocalories or 25,000 joules of heat. In the body, essentially the same combustion takes place, although slowly and by means of enzyme-mediated reactions in cells. Not all of the energy liberated in the body's burning of food is available for mechanical work. So now let's go on to section 14.6. So calorimetry means measuring heat. We've discussed the energy transfer involved in temperature changes and phase changes. Now we're ready to look at some examples of calorimetry calculations. The basic principle is simple. When heat flow occurs between two objects that are isolated from their surroundings, the amount of heat lost by one object must equal the amount of heat gained by the other. Heat is energy in transit. So this principle is really just another form of conservation of energy. We take each quantity of heat added to an object is positive and each quantity leaving an object is negative. Think of it like a bank account where you gain money by people putting money in, or you losing money whenever you make a purchase. When several objects interact, the algebraic sum of the quantities of heat transferred to all of them must be zero. And so the basic principle here is that the adding of and subtracting of all of the heat from different spots has got to be equal to zero. Calorimetry, dealing entirely with one conserved scalar quantity, is in many ways the simplest of all physical theories, and I don't disagree with that. You've got several problems here that you can work through, and you can kind of see how all of this works together. I would encourage you to do that.